welcome to this conference now. You know, everybody knows Davor Pavuna, and he will talk about some challenges in quantum technologies. I will inform you about just before 5 minutes.
Thank you, Chairman, ladies and gentlemen, dear children. This is the second lecture in the series, so I will clarify the things that I said 2 days ago. I will give additional questions. To most of them, I will not answer, because as I said in my first talk, we are community in the universe of knowledge. And toys like we use here, everything, including my favorite toy as a demonstration that you all have, we will learn about it again. And this is why I changed the title. I hope Mr. Chair doesn't disagree, because we are not talking here about superconductivity only. We are talking, of course, because I teach 33 years of superfluidity as well, with quantum fluids. But we talk also about magnetism in very subtle ways and combination of those, including the technology that's emerging. You will see it. So our scientific knowledge is not just superconductivity, or not just superfluidity, or not just quantum physics, and then every scale and applications. So it's that whole universe. Now, my own school, this is a Rolex Learning Center. It's just opposite Evian. Over here, it's Evian. These are the French Alps, actually. That's France. Switzerland is here with Zermatt, with Matterhorn. Here is Montreux, where I live, and here is Geneva, with Geneva University. All that here is France. And in our Institute of Physics, as you will see, I'll show you the full truth. The question number one is, you have to be honest. Human honesty and integrity is the number one in science. Unfortunately, as we all know, that's not always the case. Second thing here, which is important, is all in my lecture, what do you teach and whom do you teach? A lot of people ask me after my previous lecture, oh, how can you dance, teach, everything flows? Well, I teach all the time. I've given hundreds of lectures. Hundreds. 33 years of quantum fluids. I taught all of physics to chemists, but 2 years courses all the time. Excuse me, it's like Messi, you play, or Ronaldo, you play twice per week minimum. And then you do all this by heart, and I'll show you that. Also, I have great friends also here in the audience, and some who are not here, with whom I discuss. I spend all the morning with Zoran Radovic discussing some concepts. Anyway, so this is the second point, what do you teach? Question number 3, which no one usually says. It's very important when you read the papers. Who makes your sample? Do you make your sample? You will see it's going to be very fundamental. Who makes your sample? A lot of people give a talk and they make a sample. Or who makes your calculations? A lot of theorists have kindergarten boys and girls, and they give a talk. It's not first-hand knowledge. And last but not least, which way you are going and who are the people you are going with, because that also counts. Now, when you take into account these questions, then you get top institution. My 36 years here was a culture of disagreement. I agree with you. It's important. That's honesty. Culture of disagreement. I wake up in the morning, I disagree with myself, let alone anybody else. But we are nice and polite. And this I'm bringing also to this conference. So let's go step by step now and clarify all this. I'm doing my slide like I did 2 days ago. The reason is because this is simple but so fundamental. When Carl Linnaeus discovered superconductivity, he had all these elements. Carl Linnaeus was a honest gentleman who did the liquefaction of helium, even bought it specially to his uncle to have it clean so he could liquefy it. He woke up at 4 o'clock in the morning with all the team. It was not just one day experiment. Prepared everything. And then when they got zero transition, they couldn't believe it was zero. Not small, zero. They repeated the experiment. Not once. And last but not least, he gave it the name superconductivity, but he spoke to the smart guy. Van der Waals was there as well, the theorist, many others. So you can see right here all the elements which I defend, and this is the first big science immediately, because that was not a small woofy lab.
They knew what they were doing, even though they discovered new phenomenon. And this paradigm, that's exactly Manhattan Project. That's CERN. When you put all the magnets, somebody has to know what the hell you're doing. When you launch your Airbus or your rocket, there is an engineer who knows all about it. And when you have your smartphone, my dear friend, I'm not asking which model you have. I guarantee you there is an engineer who knows all about it. And here is built our knowledge. I'll prove it to you. And this is what I'm talking about. You are in these toys. You. And that starts right here, 110 years ago, with everything before. I can't go now through all the physics, which I normally teach. Now, why I take this diagram? Because it's a change of paradigm. You will see during the talk, we all lived here, at least those that are here, a certain age, and you will see. And this was one paradigm, so basically electron, phonon, BCS, whatever. These guys did woof. The woof is important, and I was alive, many people were alive, and Alex Miller had a hunch. You will see how important it is. So there was a guy who had a hunch, had a, but they had a lab. IBM was very equipped lab. The kid here, Bernard, could find all these ingredients found in the literature from France. He mixed it, he made it. They didn't have susceptibility, but then they sent it to Japan to prove it. So very serious operation, again, to the standards of Commonly Honest and the other guys. Now we'll see some other things which we have today, but then we go along and say the book. Well, I wrote that book right when ITC came along. Now I tell you, if you are married, you get divorced because of that. You don't write the book 1 hour per day. It's 24/7. And you have to know every person in the field and read every paper and every book. It's a hell. Absolute hell. Usually work from midnight until 4 o'clock in the morning. But then when you do that, and you even correct it, and don't ask me how many corrections you do, you really know the field. But then when you teach it 33 years, as I do, in many schools, then you know everything by heart. You ask me any formula, not just in here, you know it. It's because you are doing. We know your mistakes, every mistake we know, but that's life, also in the lectures. So out of that, you learn a shock. The main shock to me and everybody in the audience, because most of you were trained by physicists, chemists, maybe some engineers, but we were trained reductionist way, okay? Reductionist. Even for a hydrogen atom, you know, a little Schrödinger equation, blah, blah, some solutions. Or even the simplest case is the Newton equation for some things we do. We train kids reductionist way. And the community is trained reductionists. They have no idea about emergence or correlations or levels of reality. Nobody knows anything about it. I'll teach all about it here. And then what's the problem? But the problem is this. When you have a system, which you do, this is so famous BISCO, which we'll discuss a couple of times. To get superconducting oxide, you have to be right here. Are you with me? Right here in that spot. Within less than 1%. If you are more than 1% out, chemically speaking, your sample will not be superconducting. Now imagine, ladies and gentlemen, that in this audience, I apologize, gentleman, friend, suppose that he is not here. That he has to be there so that the lecture be on. And this is even poor precision that we have here. This sort of precision we need. When you want to have superconducting and exact doping, you are, with my apology, you have to sit there. And then when I want to go to overdoping, madam, I'm sorry, I want to overdope, you have to be right there. Now that sort of miracles we have to do in the lab until you see these things that you, my dear, can then come theoretical and say, wow, mutzi, I don't think it's a Fermi liquid, right? But it's serious. I will show you the most shocking thing in the lab that we are doing all night, and nobody says that. My dear Ali, the media don't know that. So this is the book. This is what is the problem challenge, because all of them are like that, all of them. In biology, it's still worse. I can talk for hours. And then look at this. The essence of this technology is a transistor. The first transistor, it's a big thing. It's 1 centimeter big. But the key in the transistor, let me come back. was not the major carriers. It was Bardeen contribution, minority carriers. So imagine now this room, and then I tell you, oh, you are all important. But the only important thing is this: if this lady walks through here, well, that's transistor. It's a minority carrier. Read it, teach the students. So there are a couple of things already in the transistor. We'll come back to that because we have to develop it fully, and you will understand. First of all, to have a transistor, you need something. See this? Clean silicon, I'm talking about nowadays. Clean. The secret of we are going to talk now, and secret even of my laser, is initially clean material. I mean, really clean. So let me go here. Why they didn't do immediately after the transistor, why they didn't do immediately computers? First, they had to rescale. That I understand. The rescaling happened already by Texas Instruments. That's already 58. By that time, they had Nobel Prize for transistor, right? They had to rescale, but already here had the elements were important. And then why they couldn't do it already with Shockley? And Intel did it only in 68. You know why? Brian Moore, a chemist. Brian Moore figured out the native insulator, SiO2. So when you have clean silicon, into clean silicon, you put, say, phosphorus or something, that gives you conduction, all right? SiO2 gives you insulator. So by having metallic bit and insulating, then you play Lego. So your chip is nothing else than if you played as I did as a kid, it's kind of Lego. But you had a perfect insulator. My laser, ladies and gentlemen, or your laser, it's most likely inside gallium arsenide. It has to be optically clean gallium arsenide. Only then with doping the aluminum, you get other functionality, other wavelengths. But gallium arsenide optically clean. And this here in semiconductors is the core. And this is why we had Intel, now there are many others. And then moreover, came what's called now Moore's Law. Now this is a very thing, very nice. You rescale, you make them always smaller. Now we are already in a scale that is very small scale. I won't bother you. We'll see the extension of this law. Well, we enter in with our technologies, by the way, it's superconductivity magnetism. This is already here, rescaling. We are still making scaling. You see, they're talking about quantum DNA and computing already here. And we are still resizing, all of us, basically. And then what happens next? Well, you know damn well that you've seen this before. Then you have this, and then you have Malcolm Beasley, who was actually dean at Stanford. He said, the materials drive it. There'll be even additional materials, not just what we have now. And that is a problem. Why? Because you need new materials. And then I have to bring my friend Denis Sunko, who gave a talk here 2 days ago, because he's also brilliant in chemistry. And he says, first of all, that most people missed, even Hund's rule, which I learned as a student, was wrong. And it was very important for magnetism. Second thing he says, I'll simplify, it's all serious. You have to be very cautious about chemistry of these kind of materials. You need one hand covalent and on the other hand ionic. And combination of covalent and ionic components gives you the material that is balanced in a very subtle way when you go into these materials as we do. This is Denis Sunko. And he has other things, and he's also a theorist. He really knows how to calculate these things, but understands chemistry, which is not very often the case. One good example is John Goodenough, the Nobel Prize. He's a great physicist as well. People don't know he got it from some batteries and things, but John Goodenough understands the things. But there are very few people who understand the combination of things, and this is why I quote here Denis Sunko. And this is very important also for bulk, for new materials. And this was here at the conference. I was chairing the session, but a lot of people missed. This kind of visionary theorist can give you combination that link fundamental physics and models with the chemistry in insights that are important when you do real materials. Then we go beyond. We come to the main diagram, which everybody tries to control in Cuprates. That diagram was here many times. Today, I took it from Jeff Talon. Why Jeff Talon? Jeff Talon is basically from New Zealand, knowing very well. He's often in Cambridge and a lot of things. Jeff has done this diagram very seriously. He made a calculation what's going on, what we call doping. He looked in all these kind of transitions. And by the way, 21 years ago, I gave in Cloisters the talk. In the audience, I had all these guys we are discussing this afternoon. Ginsburg, Nobel Prize winner. Alex Mueller. I mean, they were all the guys sitting right in the audience. Guy Deutscher, Morris Rice, and everything. And I was talking about pseudogap. I wish I could have given you a talk on pseudogap here. Pseudogap is not at all what we are hearing here. Pseudogap was introduced by, first of all, Sir Neville Mott in a different concept, more profoundly developed by Jacques Friedel. Then Alul from your lab put it in some context, and some other guys in a neutron scattering, and then we merged and we now call it pseudogap, and then we put it here. And the story is much more profound than we are teaching here, but I can't do all that. The reason is we have more interpretation of that, but in different contexts. Why I'm showing you this guy? Helmut Berger is the most cited person in my school. He makes the samples. When you read some kind of a paper from Dresden on photoemission or many other people around the world, they get a single crystal from him. He made thousands of them, and they're great. And all they do, usually, they do this. They take the sample and get the sample, and then they do photoemission. In 99.99 experiments are done like that, where they just do the cleavage on the sample. So they say, Uchida makes the sample, sends it to Stanford, ZX Chen does the experiment. And it's not even ZX Chen, it's his postdoc number 3. And then somebody else interprets. So it's, I'm sorry, you made a sample, you sent to you a characterization, you give him to measure, and then you over there, you interpret. Now, how can you keep coherence? And you depend most likely these days on some Asian student who then determines where exactly you are in the diagram and what the hell is going on in the sample. And they didn't measure all the properties. They didn't. I'll show you now on. We discovered it in our lab. We love Helmut. And then the director of the lab at the time, Laszlo Fora, we looked at the samples. He measured doping versus disorder. So we noticed that samples we send around the world, if we do measurement just resistivity, nothing else, just resistivity, constant resistivity, they're different. They're different if we change what's called doping versus disorder. Because Florence, your dear friend, a colleague, late colleague now, she did bombardment. So in these samples here, they were made in the lab, they were not bombarded. And these, of course, there's a doped and these are bombarded. When we bombard samples, we introduce defects and you have different resistivity curve. If you would do just angular result photoemission, you wouldn't see it. So that's when we learn big lesson, that even the lab where we have it, you have to combine surface methods with the bulk methods and full characterization. It's like if you analyze the conference. It's not enough to say, oh, I have here on the spot 140 scientists, we are about maybe 1,000 worldwide, blah, blah, blah. No. The government will ask you much more. Which nationality is present, all that, you will analyze the profile and everything. That's like here. If you really want to understand, you have to layers deeper, and this we realize then. And that, when I realized that, and I can give you another talk on that, that disillusioned me. And I love Helmut, we even published several papers together, but then I decided to go a different route, which Neven Barisic summarized very well. Neven Barisic did his doctorate with Laszlo Fora in Lausanne. And this is basically the state of the art in understanding what you would call Fermi liquid extended for the phase diagram. And because he gave a talk, and we'll summarize it, I'll just basically say the following. He analyzed single crystals. He had single crystals on land. He went to Stanford and Minnesota, learned how to make single crystals, made his own single crystals. He measured them. He analyzed them. He knows this inside out. And he discovers Fermi liquid in these materials. And he discovers the importance of localized hole and has a different interpretation of the phase diagram. Okay? Now, if he were a theorist, as his father was, I would worry, but this guy is a well-formed experimentalist by my friend and colleague Laszlo Fora. Everybody knows it. Well, he has very, very good measurements, and he made his own single crystals. This guy right now is a problem to the whole community, myself included. If he's right, we'll have to rethink, because certain results in his approach seem to be relatively simple. Yet we do not have the final answer. I'll cite him again 2 days from now. So Neven has a story that I discuss a lot with several friends of mine, Ivan Božović, Zoran Radović, all of you here, and so on and so forth. I'm not saying it's final, I'm not saying correct, but he satisfies the criteria. Beautifully formed, worked in Stanford, Minnesota, Lausanne. He's professor in Vienna right now, in Zagreb. Guy knows the show. He knows the job. He did his stuff. He does everything. He has different story than we do. So follow Neven Barisic. And I'm not saying I agree with him. And he's a really good friend. Science is very demanding. So let's continue. Why I went with Ivan Božović? We studied in 1994 nanoengineering of superconductors. You remember what I showed you about transistors? By that time, we had first computers, we had first chips. So we realized one line of computers will go in that direction. We called it nanoengineering. And then on top, Ivan convinced me to do something which is incredibly difficult. And I don't advise anybody else to do it. I spent years and years in the United States of America. I was resident in Switzerland. I was living in Switzerland. You know where you live. Well, I lived at Geneva Lake. There were my small kids and wife. And I was flying to Wisconsin. I came to Wisconsin. They had a synchrotron. We didn't have it in Switzerland. There was nothing there for my experiment. From zero. I mean, zero. I brought the money. I brought the team. We built all this that you've seen in the diagram with my student, Mike Abraham, and several other guys. We put it in the tent. It was laser ablation. So what you do, in one chamber, you, just like MB, you make the samples at a high temperature, 1000 Kelvin. Then cool it down. Wait 1 hour, oxidize. Then you move it to the other chamber with the hand, cool it down to low temperatures, check the vacuum, and then you do the photo emission to vary the sample and measure it. All the referees said it's not going to work because you will have polluted surface because you are not doing the cleavage. True. Seven years. I was reporting negative results to Swiss and American National Foundation. Everybody funded this. But they started laughing at me. This is too difficult, it cannot be done. Well, it can. When Mike finished his thesis, when we proved it can be done, Alex Mueller in person came to his thesis. Alex Mueller, the guy who invented this, right? And the automobile. When I gave a talk in Shanghai in 2009, the whole audience was applauding. They copied it. They have it everywhere now, okay? From Yokohama to Brookhaven. They even added now the STM. So you don't do the lab any longer without doing materials in situ. And I'll show you the consequences of that. And that's why they ask you why you not all the time in Lausanne. You will see because of that. We did it in Wisconsin. Now you have that also in near Zurich, in Willingen. Now, if you build a new lab, you have to have this. You have to have everything in situ. You make your material, you measure next door. Not like that, not in Berkeley. In Berkeley, in the early Nano Center, they made materials in one floor. They did characterization in the second floor. They made something measured in third floor. Then in fourth floor, they talked to the professors. No. The moment you bring the sample to the air is full of humidity. Air is full of carbon. It's not just COVID, for goodness sake. Scientifically speaking, air, particularly in the labs and wherever we humans usually go, and particularly our mouth. You know that the most dangerous thing in the universe is French kiss, mouth to the mouth. I'm not joking, actually. It's biologically still unclear why a man and a woman can kiss and not die, literally. Now, in technology like that, that's hell. We built another instrument, Lausanne. I won't bother you with that because we've done a lot of that. It's very difficult. You remember what I told you have to make your samples? You know how many nights we were in the lab? You know how many bad experiments we had? Okay, ladies and gentlemen, a lot of people say, oh, you're successful. No, I'm a failure. You know what is my rate of success? You know how many samples we studied? And not just me, Ivan Božović, totally independent. Our success rate is 1 in 1,000. We are lucky. more like 1 in 1,000. Which industry will you tolerate with success rate 1 in 1,000 or 1 in 10,000? You go to industrial guys. Ask them. We are incredibly inefficient, expensive, lousy, difficult, virtually impossible bunch of people. And you see one of lunatics, right? My referee was Hans-Rudi Ott from Zurich. He's a brilliant guy. You know what he said to me? Davor, all the referees say this cannot work because the service policy. But science is a risk. That's why we'll finance you. That you can do in Switzerland. That's why I am in Switzerland. In top laboratories, when they went to STM and IBM, I spoke with Rory Binnick, with Alex Weir. In top laboratories, they go for high risk. Behind you is your dean. Behind you are your colleagues. Remember what I said in the beginning. You teach, you go, you have integrity, you fight for the ideas. And then it's still years until you get the results. And nobody says that. They tell you when you get Nature or something. Writing a book, getting this kind of results, it's years of work, day and night. Much more difficult than any other ballooning they tell you, including astronauts or management or whatever. I can guarantee you. We can compare. Now, Ivan did, because we're friends, we discussed all that, he did his miraculous thingy in Brookhaven. I've seen his previous models. We know each other for a long time. We discussed a lot. So I won't go into it because he gave a brilliant talk. He put his questions, he analyzed. In my humble opinion, he's a candidate for Nobel Prize for various things, including two-dimensional superconducting proof, for interface superconductivity, for several other incredible results, including theoretical insights. But we had a great compliment for Yulu. Yu is one of the presidents of Chinese Academy. When we were both in China, Yulu said exactly that. If the material is emergent, which it is, an emergent property is superconductivity. It's not just one electron, it's a collective property. When you have something like that, and emergence is actually a phenomenon we have also in magnetism, many other phenomena which are relevant to that. You need control. And this is why we went to this direction. And this is why my talk will lead you to some incredible things until we come to the end. Because you have to make your sample. You want to have good theorists, which we'll see, you will add on. You need the theory, of course you do. Brilliant technicians. You know what do my technicians in high vacuum? They repair Rolls Royces at home. That sort of technicians I have. They can repair molecular beam epitaxy like that. So that's you need, but to get correlated quantum matter completely, you need all that. So it's a much higher level than commonly honest. Remember the beginning? All that you need now in top laboratory. So what's next? Well, we've done it. We've done with Ivan. It's now Nature 211, but look at that. Here is a superconductor. Here is an insulator. And you can see beautiful transition. It was my doctoral student, the GDB with Ivan. That was easier than the previous experiment I showed you. This we have done within 2 years. We were literally sitting at a beach in Caribbean islands when we decided to do that. Guy went over, we were ready, we had the sample, Ivan knew how to do beautiful samples. So this was Nature, but it was only 2 years of work because we knew all the rest because of previous 20 years. I had the brilliant guys. But I still have to tell you this. The paper published in Nature, listen to this, was version 53. And we are senior people, we experienced, okay? Now, last night we had discussion, Ali remembers, we had a discussion how to teach young people to write projects. Excuse me, we were all mature, experienced, 53 versions to write to appear in Nature with a clean result. You don't see everyday curves like that. And we checked all that. And now we are not kids. This is 211, for goodness sake. Since Stanford 1988, look at where we are now. Yes, we get into Nature. Then the people, of course, repeat it. But look at the amount of work. We are hard-working guys in the mines. Yes, you see me here at the beach. Here, yeah, maybe 1 hour, 2. Most of the time, it is incredibly demanding, highest level integrity, top. And you have to know everybody in the field because everybody counts. You all count. You all count. I cannot tell you who will come afterwards to me or the other way around and see, look at this one, look at that. It's a community thing. But then what's next? Well, you remember Moore's law. Now we have another curve like that. And we have a lot of people, of course, but we have still improvements in this area. And then we have something called Kurzweil-Singularity. If you look at this kind of thingy, well, let's come back now. I have to come. This you have to understand. It's very simple. If you look at the human intellect over the centuries, this is what Homo sapiens was all about. It's going like that. The guys who are now making what's called artificial intelligence, which is like little Siri in your phone or some other things. This is not yet true in artificial intelligence, because true artificial intelligence means that machine writes code for the machine. But doesn't matter. Kurzweil is a very smart guy. He made keyboards and lots of other things. But Kurzweil, above all, is actually strategic director of Google. There's a lot of money and a lot of options. Eats mainly tablets and wants to survive. I don't know. I think he wants to put himself in the refrigerator and re-emerge in the liquid nitrogen, his only mind or something crazy like that, but doesn't matter. But Kurzweil calls this singularity, and singularity, just remember that, because there's driving a lot of this technology. Singularity means, listen very carefully, that machines, robots, and artificial intelligence becomes on average more intelligent than humans. So it's not when Japanese or IBM or somebody says, oh, my computer won against, champion. It's not one computer. It's not one thing. It is when on average we have 8 billion people, right? And on average, robots, machines, or whatever you want to call these entities, but non-Homo sapiens entities, on average become more intelligent on average than we are. So according to Darwinism, finished with us, right? Because you would expect new species, even though probably made of silicon or something, they need just only energy. The first thing they don't need women, right? With all due respect to women, I would certainly be more in favor of women, female civilization. But this is called singularity. Well, they said first 2031, which is around the corner. Now they say 2045. So it's highly controversial. There's a big debate about it. Nobel Prize winner Roger Penrose thinks that they could be completely wrong, because big question is, do the machines or can they develop consciousness? Because we have them. So this is an open debate, but that is not what I'm talking about. I'm talking about just because of dry technology, okay? Because there is now all of Silicon Valley, pro satellites in China mainly, with huge money. I mean, huge money, where they just don't buy you for a professor salary. If they want to buy you, they buy you with the whole lab, and they do. With 100 million, you and the whole lab. Not only once, I know several people, and they even offered to me. They buy you out. They put you in a new lab to work for quantum computing and other area, and all this area, and dominate quantum technologies, as I described, and many others. And this is no longer assistant professorship competition, as we discussed yesterday. Assistant professor will hire you, go through 10-year. They buy you, actually, they would buy you as a mature professor, full boom, chup, tap, and they move you from, wherever you put you to California. You get all the toys that I will show you. You get them all. The salaries are mind-boggling. That is no longer academic salary. It's a dream, but you work for them, right? Now, that will determine when do we have this happening. It should happen in this century. I'm personally much more in favor of humans. This is why I like to belly dancing, tango, I like to sing. I'm more Humphrey Bogart than Ingrid Bergman, 1951, but I have to warn you about that. And this is why quantum technologies and Kurzweil singularity, which is expected here within half or one generation, they push what's called transhumanism agenda. They can chip people, they can put things in. They claim it's all very good for us. Maybe it is. I don't know. But I'm very happy as analog human, And I love women. I love love. I love poetry. I love music. Now, what kind of entity I become after that, I don't know. This is going on. Ideology of a lot of people in Silicon Valley is this. I'm not even fighting them, but we are part of it again. So let's continue. As I told you, we had in 2007 a meeting in Norway, paid by Americans, everyone's paid, 5-star hotel. to make room temperature superconductors. There are a lot of people here. Some of them are no longer among us, but I won't now mention and so on. That's not the issue. The issue is that we were paid to discuss only one thing. Yeah, I'm finishing time. And the challenge we realized then, it's not this scale. Because, well, you know, this was this and then this. But challenge the students, we have to get above 300 Kelvin. We have to get somewhere here. We need operational superconductors on any scale, a large scale, medium scale, intermediate, here. So they ask all the people there, what do you think? And I'm sad to tell you, one of our stars left this world 2 days ago. Ted G. Ball was a great, honest gentleman. He didn't have to do science. His wife is one of the owners of Levi's factory. So actually, even the buildings in Stanford are called G. Ball Labs, all right? Ted G. Ball passed away, age 102. Had a remarkable career, I just said briefly. Ivan Božović wanted to give me even a longer talk on him because I knew, because we even gave him a prize a couple of years back at some conference we shared in California, and I knew him well, okay? But that guy was going to the lab up to age 100. Really, we have photographs. I didn't want to. Here you can just see him. He's actually even giving a lecture. Here is 97 at that time. Ted G. Ball was coming to the lab, even during COVID and everything. Remarkable. He used to be in the Bell Labs in the golden generation where we're doing all those old materials. He used to organize a conference way back in '88 called KGB, Kapitnik G. Ball Beasley, on new superconductors. He was very well informed. You could talk to him anytime. But he was a legend. No, he didn't get, to the best of my knowledge, I don't think he got Nobel Prize, but he's one of the close fellows. He was also in Lyon. And this is what he suggested. So it was very interesting. That was his summary of his talk. I had all these talks, so it was very nice. He believed in this oxygen. He followed U pairing centers and some other things. And he said, prepare Ribeiro Pasteur to be lucky. So a lot of these people of that caliber believed in hard work, consistency. And yet another example. In his samples, they made samples. Yes. In the collaboratory, yes. He spoke with the theorists, yes. It's yet another example of high integrity person. Well, Bell Labs went to California, and they form people that then create all these other fantastic things. So now this brings us to the final. So what are we going to do next 100 years? And that's why did I have some divergency with my own physics department. The reason is because when I knew all that, I said to my friends in Lausanne, I need a new building. 50 million, 100 million. Are you nuts, Davor? They've done all that. I said, we can't do what we are doing. Why? Because we have a train going next door. Zoll, it's called, you know. And then you have vibrations. Now, what do you do if you do the STM on your surface, right? Now you're doing it here, and there's vibration there. How do you do atomic resolution measurements? And you are vibrating, which of course you are in our scale. So luckily, on quantum computing, you heard Japanese. They already know that, of course. Then luckily, Klaus Kern, who is also a professor with us in Max Planck, he got the building. I went to Stuttgart. I said to my chairman, look, they have it in Stuttgart, because Max Klaus, he knew it. Klaus Kern knew, because he did STM, that he needs a building that is levitating. 50 million just for the building. Well, my boys are smart, so Lausanne, this is how it looks nice. He's getting a new levitating building as well. They call it Office of Science of Light, doesn't matter what the name is. And you will see all your labs, if you are well-funded or well-visionary, you will have to have levitating labs. Yes, darling, in Orsay and whatever you want, Sackler, whatever. No way you can do it all the way. The era of commonly honest had already the elements for the age, but now, no. A physicists measure, no. What do we measure? Gravitational waves. You remember I think the amplitude was of the order of an angstrom or something, wasn't it? And they were kind of two black holes, you know, sniffing each other, and you need that. So this is your future. They ask me, what is going to happen here? This is going to happen. You asked me yesterday about the funding of superconductivity. What did I answer? Hundreds of millions. Quote me. You cannot do quantum technologies as we used to do physics when I started 50 years ago or even something like that. No way. You need STM, AFM, inductance. the things that my friends and myself have done it. I won't go there. I have much detailed talks. You have to have all of it. Small science is beautiful. You can think very well, but you will have all it. You will even have, because you asked me that as well. You know what you will have? You will have we discussed that as well. Yes, you will have a theorist with computers plugged into it, and the growth, Chinese actually already offering to build it, and the growth will be done as artificial intelligence help calculations of chemistry structures, and you build those materials the way Ivan Božović does, but all automatically. And then you will have all the characterization measurements, and this is all going to happen in one generation right now. I'm telling you that right now. So you remember when you and me meet at this conference, which will be, what is now, 7? What is number now? What number you have now? We know because of COVID. But okay, let's make it 17 or something, whatever. At number 17 or whatever, 70, whatever. You will see that I was right. I do not go to China unless they give me levitating lab with the budget I won't even mention. Forget it. You can't do it. You can't do it. And they have that sort of money. Apple Computer is right now $2.5 billion, and Apple needs it. So that's our future. And now the best important thing is, it's not me who counts. It's not you. It's not you, my dear friend. Our students dream it. When you have students who want to go for it, then it's easy. Because they do it. You can put the toys. Yes, they cost you. They cost you once. But the governments and they have that money. They love, the presidents love the building. My president, my bosses, they sleep until 10 million. 10 million, 50 million? Because then they go to the newspapers. The New Light Center, beautiful. They'll be everywhere in the newspaper. But you know, still need humans. Late Øystein Fischer said at that meeting in Norway, and I love it. If you really want a new material, new breakthrough, you need Alex Muller. Great nose. You still need humans. You still need theorists. You still need the ideas. So you see, I'm also partly wrong. You don't just need big science. Of course, it's necessary for this part. But also at the ideas level, we are back to Landau. We are back to Bohr. Remember all those big schools? We are back to Planck. We are back to Helmholtz. We are back to the smallest, beautiful Pierre-Gilles de Gennes. So at the end of the day, we need both. We need great directors like Karajan. We need great philharmonic like Berlin, some others. Great opera houses. We need the combination. So yes, my dear friend, this is why I love this conference. Nominally, we are probably 1,000 correlated worldwide, and the news go beautifully. But here we are roughly 100, 140, which is good, gives a coherence. We can fight. You don't have to agree with me. I don't get cross. If somebody says I'm wrong, I'm perfectly happy. I'm often wrong. Yes, sure. I don't think I'm completely wrong, because this is my life, my direct experience. But this is what I think is going to happen. I'll give further comments and things in the final panel session 2 days from now. But if you allow me, I just have to tell you, we have more conferences. Actually, I'm one of the chairs and organizers. It's actually in Tuscany, in Italy, in June. I don't know whether it will happen at all, but it's fun as that I tell you. And we also accept people and smart ideas. This is an easier conference. It's mainly in ceramic context. So you're most welcome also to Italy to this ceramic conference. Thank you very much.
Thank you, Professor Pavuna. Is there any question? Okay, Ali, please.
Thank you very much for the very visionary talk. But the near future issues, I think, are becoming more impact research, especially for high TC materials to be on applied science. One of the critical issues, still materials are not mature enough for technological, let's say, large scale penetration. That's the
Yes.
applications. So, okay, you may not need floating buildings, but you need high-tech laboratories working on applied sciences.
Right. I can give you good news. I'm very grateful to your question because not everybody has to go this way. I agree. This was the vision for a department that wants to go kind of ultra thin, ultra small, ultra films or whatever. You're absolutely right, and I prove it to you, but I can't do everything. It's too short. You're 100% right, and but the trends again go in the other direction. Actually, the fine tuning, let's call it of in the interface and the material, including, let's say, artificial intelligence that can be now done in quantum chemistry, will help you that you will have much, much more profoundly fine-tuned chemical materials. So, which is not in this talk. I couldn't do all of that. So if you suppose you go to the bulk route, and suppose you're like my friends, and actually we have that as well in Lausanne. We have actually a center for doing that as well. But then at the end of the day, you need people who will make them. And what you imply is that you would like to have, so to speak, critical lens under control, because not all the materials are compatible with the knowledge that we have.
What about your views that
My views on big data and artificial intelligence are very clear. On big data, we already have basically that approach. We can't avoid it. Just to give you an example, let's not talk about Turkey. Let's go to Germany. In Germany, even if you die, your health data are secret. Okay? And this is a big data. If you go to any military operation, the data, of course, secret. Most people maybe didn't realize, but when recently in Afghanistan, there was this Taliban taking over of the whole place. One of the most important things that some media reported, and they took all the database of American military, including the DNA and God knows what. Very tricky. And then getting to the core one, which you don't know, because we don't know these things. You know where we are most sensitive? It's insurances. Whether you like it or not, none of us can be here one way or another without having any. You are bound to have at least some insurance, with your health insurance, with job insurance, with whatever. So in Western countries, and those of us that are here, most of us have one, if not three insurances. Now, the insurances guys tell me that the level of crime that is about 30%, this is very critical. And I can tell you, I certainly had a couple of times that they've entered my credit card. I know people who they had even the identity taken over and many other things. So the most critical issue in big data is the protection of those data. And it's not military thing. It's really even down to earth. And it also touches all of us. And this is why I mentioned that in the previous talk that, okay, there is a patent of a young kid in Lausanne and so on, or how to do even quantum computing protection and so on. This is a very important thing because we have $19 trillion business already in that area. And to complete it, show that you are right, material science of the future, and you implying that, is big data. So they will push it not because of us, Ali, they will push it because of them. Yes, but then because we are, and they like us because we are good for the media, and when we put some of these things, then they want to work and collaborate with us. So I'm basically the optimist. For this community, I'm an optimist because they suddenly love the buzzword now is quantum. They don't understand anything about quantum, but they like it because that gives them importance. Oh, all the politicians like the importance. So if you take to your president, you have magnesium diboride, which we can prove, and it's Turkish, and we can do Center for Magnesium Boride and Related Technology in Turkey. He will love it. And believe me, for them, 10 million, no big deal. Did it immediately. So I'm very great optimist. It will take time, energy, and vision. Same by those.
Thank you again. We have already exceeded the time. Okay, one more.
Could you comment the difference in RPS or other measurement for
Yes, of course.
single crystals
Yes,
for
Yes, sure.
lanthanum based or maybe bismuth
Of course.
based
All of
as,
them.
sorry, excuse me, grown into the chamber of your device
Sure.
or grown in another lab
Yes.
and then cleaved into the
Yes,
chamber?
I can. I can give you I gave hundreds of talks on that in detail. I make it very simple for you. Suppose you have a brilliant crystal grower like we have in Lausanne, okay? And there is like Uchida in Japan. They have beautiful single crystal grown in the lab. And then in the same lab, they do, the cleavage in high vacuum, and then they measure. Here you will get a very clean surface. You can do the STM, you can do RPS, surface techniques. But make no mistake, it has to be very high vacuum, it has to be very quickly because the surface will still recombine and the surface is never bulk. So you don't see interior bulk. For that, even Božić and other people, including myself, use kinetic inductance method invented by Vitaly Gaspar. Now, between MB of Ivan Božić and my laser ablation and similar things which I developed, the amount of disorder is a problem. I cannot get that high a vacuum. So molecular beam epitaxy that Ivan Božić uses, he can use also ozone, which can I as well, but I have much higher degree of disorder, chemically introduced disorder by growth, because laser ablation is a pretty brutal process. Molecular beam epitaxy is more like gentle. You deposit layer by layer, nicely, gently, slowly. In laser ablation, you do it, but it's still more brutal. So we have higher amount of growth-induced disorder, okay? Now, we don't have to cleave, because we've developed it now without cleavage, but we have to be very cautious what is the top layer. So with the buffer, we control what's going to be the top layer in our growth, which we know by now. It's a lot of experiments. We learned that in the last 10 years. So we can also get to the top. But by and large, MB is always better because it has less growth-induced defects. Now, the question is then, would you still cleave our samples? And the answer is very difficult. We try to do that, but that's very difficult because you're really dealing with the very small quantities and doing the cross collaborations and talking to other laboratories, because many people now do it, we have come to the conclusion that's not necessary. So to simplify, if you want the clean material, the way we can do best, you use molecular beam epitaxy, probably assisted by ozone. You need very good people, very good control, a lot of patience until it's stabilized. If you want to have quick and dirty, you can do it with laser ablation, you can improve it, but it will not have the same level of intrinsic lack of defect, so to speak. For field effect, then even more important that you do it, let's say, in very good single crystals that are properly characterized, and above all, of course, in molecular beam epitaxy materials. And we can scale that. We have all sorts of papers and things to discuss.
Thank you again.